Hey everyone, so what I'm going to be doing in this video is pretty much just going over all the material that we went over in the exam review. So in the event that you didn't get to make it on Tuesday, earlier today, then I'm pretty much just going to be going over the same things that we went over in that review session, and everything that we went over is pretty much this here. So we spent some time looking at simple machines and maybe some problems involved in inclined planes, pulleys, the three classifications of levers, and all this great stuff here. We also looked at vectors and computing magnitudes and direction in the x and y components for forces, and for just like how we had two forces acting like on a point, just how we saw earlier today. Well, earlier today meaning Tuesday in class. So we also looked at essentially the resultant vectors of magnitude and direction of those forces acting on whatever object or point it was. Ethics, we didn't really go over much about ethics because I know we really didn't touch on ethics in lecture. Either I wasn't there, I guess, but I really don't think we even went over ethics. I think one of the students even told me that apparently ethics is somewhere like in next week's curriculum. So in the schedule, I think not next week, but the week after. So the week after Thanksgiving is when we're going to go over ethics. So I don't know, that might be true, it might not be, but I really don't remember going over that. But we kind of just said, read your book, see if there's anything on ethics. And I mean, what I would do if I was a student, I'd probably just, if I saw ethics on this review and we really didn't go over it, I wouldn't worry too much about it, but I would also just go in the book, see what there is on ethics, on engineering ethics, and maybe look for like a summary and see what information is there that I can maybe get out of to help me with the exam. But yeah, that's as far as ethics. MATLAB, we did talk a little bit. We talked about MATLAB and some of the things that you can do in MATLAB. It's a lot. We did a lot of things similar to the homeworks that have been assigned, or the assignments that have been assigned. And then we finished off with free body diagrams. So these are the main thing. This is everything that we went over. So it's all right here. And I'm pretty sure I emailed you this already. If I didn't, or no, I haven't yet, but I think maybe by the time you see this email, you probably have already had that email, so, or this thing sent to you. Okay, so I'll just stop. Okay, so first thing, like I said, make sure you remember what these are. So there's probably going to be a question on the exam that's going to ask you, what are the 6 simple machines, or name the 6 simple machines. And what you're going to have to do is essentially just write down these 6 here. So inclined plane, we know inclined planes are like, I don't know if there's like a shape here. Yeah, they're like this, right? So we have like a ramp kind of thing, and then we have a certain height here, certain length here, a certain length here. And then we can use equations such as ideal mechanical advantage and actual mechanical advantage to determine things like efficiency of this inclined plane. I'll get into that here in a little while. Levers, like I said, this review says there's 3 classifications. So literally, if you just go into Google and type in I don't know if it was this one. Well, yeah, I guess this one works too. So here, class 1 lever is essentially the load on one side of the fulcrum, and the effort is on the other side of the fulcrum. So if you imagine just like this piece of these pliers removed, so let's say we had like a little triangle here, and we put effort here, and we had a load here, then if we can, with this lever, we can put not as much effort here to lift a large load here. But that's kind of like getting like into like a seesaw kind of thing. Let's see if I can draw it here. But I think you guys have like probably a good idea of what it actually is anyway. So here you have your effort force. Right here you have a load, or a I don't know, a weight essentially. So this is what is to be considered a class 1 lever. So if we look into class 2, class 2 has the effort and the load both on the same side. So if I switch over to, if I just move this around pretty much, but this is the other way. I don't know, it's supposed to be vertical, but imagine that this is vertical. So your effort force and your weight or load are essentially on the same side. So you do have, again, you do have mechanical advantage here based on this lever. But when we look at lever 3, class 3, these are essentially switched. So now there's the least amount of mechanical advantage here, but if you think about it, if you're lifting from this point and it's rotating about this point, so if you're lifting this weight here from here, let's say when you lift this like this far, just this far, this will move maybe twice as high, or depending on what the length of the beam is, or I guess the distance between where you're lifting it and where the actual weight is. But that's essentially the third class lever. So let me delete this. Not that. This. Okay. As far as pulleys go, we did see a lot of pulleys. We did a whole workshop on pulleys, obviously. So sure, this will be so like that sawhorse that we had. So this would be like the top. See if I have a pulley here. That's kind of big. Well, let's forget about this one for now. So let's say that there's 2 strings attached here. Oh no, I want something else. Or there's a string attached here. And the weight, whoa, that's not what I wanted. the weights here. So let's say this is a weight of, can I type in this? Oh, yeah, I can. Okay, so let's say this is a weight of W. So W is distributed by these two strings here, or rope, whatever you want. So it's distributed evenly, so we can say, this is assuming that this is both vertical, both of these are vertical, so we can actually say that this does what it wants. In front, I guess. Okay, we can say that the tension in this string is felt, if you measure it, it's essentially 1/2 times W. And the tension in this string over here too is also 1/2 W. So you're essentially splitting, so if you're pulling here with this string attached here, you're pulling a weight, you're pulling half the weight essentially. So that's the good thing about pulleys. Now we did talk about the ideal system using 3 pulleys, and if you remember, it involved having another pulley here, having this string tied to the center here, it involved essentially this. Okay, so now keep in mind that we're still experiencing 1/2 of the weight here and 1/2 of the weight here. So if everything was like nice and vertical, let's assume that this, if we assume that this string or rope was vertical, then we can also say that it's pulling down here 1/2 W. So what you have in each of these is okay, 1/2 of 1/2 W. So we have 1/2 of 1/2 W in each of these strings here. But 1/2 of 1/2 W, I mean, just simplified, is 1/4 W. So that's pretty good because we've already reduced it to 1/4. So if this was like 10 or something, this would automatically be 2.5. If this was like 10 newtons, then this would be, what you'd be pulling up would be 2.5. Okay, and if I do it one more time with the very last pulley, then you'll notice that we'll be cutting this 1/4 W in half once again. So So this string here would be filling 1/2 of 1/4 W, and this string here, which you're pulling up, you'd also be filling 1/2 of 1/4 W. So that's pretty much the example. That's the entire example that I went over in the review. So just keep in mind how weight can be reduced. Obviously we reduced it greatly here, because here, I keep pressing the wrong button, here we only have 1/8 W, which in this case, if W was equal to 10, oh my god, you can't even see that. Okay, there. If W was equal to 10, then this would be 1.25 newtons. I don't know. I think the majority of you understand what I mean. Okay, so next, as far as screws go, we really didn't do problems with screws. We didn't do problems with wedges. I really don't think we did problems with wheels and axles. Let's see, as far as computing mechanical advantage and all this stuff, through using inclined planes. Where is it? If we have like a box here, and let's say this box was 20 newtons. I mean, this is just like what we saw in class, and this is exactly what we went over in the review. We found values for ideal mechanical advantage and actual mechanical advantage. So let's call this A here. This side here, let's call it A. We can call this side here B, and then we can call this side here C. So remember that ideal mechanical advantage is equal to I believe the value C in this case, which is essentially the length of the ramp itself. So, and it's divided by the height here, so B essentially. So you'll get some value for this, so I'll just say height of ramp. Actual mechanical advantage is denoted as the force of the, or not force, well, it is a force, but the weight of the object divided by the force required to get this box across this ramp. I don't know, I'm just gonna I'll just say that. But in class we had something, I mean, this is exactly what we had in class, right? So we ended up with 20 divided by 4.2, I believe it was, because 4.2 was the force required to push the box across the ramp. So we ended up with some value of like 4 point something. So so now we have values for IMA and AMA. So now our efficiency, which is denoted as the symbol eta, is equal to the actual mechanical advantage divided by the ideal mechanical advantage. So this number should be less than 1. So you'll get I think in our case we got, what, 0.7 something. So as a percentage, if you wanted to get it as a percentage, you just multiply it by 100, right? So we'd get, like, I think it was 74% in class. I can't remember exactly. But efficiency is denoted as this. Eta is equal to AMA divided by IMA. Okay. I'll delete this stuff here now. Okay, so I would just go over quickly. Work is equal to a force times a distance, and usually the units are in Newton meters, and they're written like this, and that's for SI units. Or they're also in we could just say pound-feet. And those are in English. So work is, I know, like earlier in the semester, or earlier like in the weeks, maybe even this past week, we talked about moments, and moments are essentially the same thing. They have the same units. I mean, work is different in the sense that you, like, if you have like a box over like a floor or something, like, let's say this is the box, and you push the box X amount of meters, and let's say you somehow had the force to calculate what was required, then that in a sense is work. But a moment is, like, if we looked at, it's kind of like going off topic here, but if we looked at, I think, was it class 1 lever? What we are dealing with are essentially moments, right? Because we can have like some distance. We can have distances like x from here to the fulcrum and y from the fulcrum to the effort force, and we know that this has some kind of weight on it. We know that we're applying some effort force on it. So in this case, our moment would be our effort force. We'd have some value for our effort force, multiplied by whatever length we got by y. And on the other side, we'd have whatever weight this is, because technically this weight would also be a force here, because I mean, if this was like 20 kilograms, we'd have 20 kilograms times gravity, right? Which is 9.81 meters per second squared. So in that sense, that's a moment. So if there's any confusion there, because they both equal the same thing, so, but they're not technically the same thing. It's a little confusing, but if you're either, I think, a CE, an ME, an AE, I think maybe even double E's take this stuff, or you're doing like engineering physics, then there's a really good chance you're going to see all this stuff. So I guess it's kind of good to get it cleared up now. Okay, so we're done with that. So moving on. So vectors, computing magnitudes and directions. So this is where it's kind of confusing, because I know if you happen to be like in Math 121, or you haven't, whether it be that or whether you haven't been exposed to cosine, sine, tangent, all those trigonometric functions, all the trigonometric identities, everything having to do with trigonometry, it'll be pretty hard trying to understand this stuff. And I know that because, I mean, if I wasn't exposed to it, I know I would have a really hard time understanding all this stuff too. So let's go ahead and look at an example. So let's say I have this force here, and then right beside it I have this force. And then I'm also going to draw my horizontal. Oh, I think I deleted my text box. Okay. Maybe I should have had all this stuff formatted, right? Okay, so let's say that this angle here is 30 degrees. Let's say this here is, I don't know, 35. And this, I'll make this dashed. So we know it's not really part of anything. So what these forces are pulling on, this little point here could be anything. It could be like from, I don't know, let's say you go out to, I'm from here, so let's say you go out to Elephant Butte, you get stuck because, I don't know, maybe your truck doesn't have four-wheel drive or something, so it doesn't matter, you get stuck. And there's two other trucks who tie ropes here, and they're both pulling to try and get you stuck, trying to get you out of the sand. So that's one quick example of where you would see something like this. So next time you go to Elephant View, you'll know. And I don't know like how exactly useful it would be, but you'll know. So okay, so we gotta give these some values, right? We gotta give these forces some values. So let's say this is 50 newtons. Oh, no, not 50. If we're pulling a truck, it's 500 maybe? I don't know. I don't know my conversions very well. So let's say this is 300. Okay, so probably what you're going to be asked is to find the resultant force. So just by looking at this problem, you can already tell that this truck, whatever it's doing, is there a truck shape here? Or a car? No, probably not. Whatever this force is doing, it's going to be more significant than this force, right? So you'll have a resultant vector somewhere like right here, pointing like in this direction. But I can also find out what exactly that resultant vector is by taking this same arrow, the same 300 here, placing tip to tail, and then redrawing my new vector. So bam, there it is. So this is the resultant vector. So you'll get something that looks like this. The numbers will tell you, the numbers tells you one thing, but actually drawing it out shows you like where it exists. So that's just to show you maybe some more meaning. So okay, so first thing we have to do is we have to break these up into components. So this is kind of where it gets a little difficult. So if we forget about, let's forget about this for a little while. Right now I just want to look at this here. So in order to break this up, I need a coordinate system. So let's say this is not like, I don't know, whatever. Okay, so let's say that this is y. Going up in this direction is positive y. So keep that in mind. And going right in this direction is positive x. So keep that in mind. Yeah. Positive x. And positive y. Okay. Imagine these are arrows, I guess. Here. There's arrow tips right here. Okay, so in order to break this thing up into x and y, I need to know a few things about trigonometry. So I need to know how I'm going to utilize this 30-degree angle in order to get my respective components. So there it is. So my y component will look something like this. I have no idea why it like snaps. It's Okay. Let's do, yeah, okay. That looks pretty good. So here is my y component. This, we'll call this, let's say this is F1. Remember, this belongs to this, so this Fy of 1 is going to equal some number which we'll calculate. But in order, so here is where we need to determine what exactly we're going to use. So if we're going to use this degree 30 here, and we're going to also use trigonometric ideas, functions, I guess. So what would be useful to us right now is SOHCAHTOA, which means sine is essentially equal to the opposite side divided by the hypotenuse. Cosine is equal to the adjacent side divided by the hypotenuse. Tangent is equal to the opposite over the adjacent side. So really, what does this even mean? I mean, if we have an angle that we're looking at, so we do have an angle here, and we want to find this side here. This side here is opposite of this angle. So if I was looking at this angle here, the side that's opposite of this angle is this side. So we're assuming at this point that this is a right triangle. Here's the 90 degrees here. If we're looking at this angle here, the 90 degrees, it doesn't even matter. The opposite side would be directly across. Okay, so we're now here. We're at this angle, and if we look directly across from this 30, the side is here. The side that we're looking at is here. So when we're using SOHCAHTOA, I mean, let me just write it out. Sine of 30 okay, sorry. Okay, so sine of the angle 30 is equal to opposite. By opposite, I mean like a numerical value. So what we're saying is like that if this arrow were a length, it would be 500. So we don't know the length or the force of this here. So we're just going to call it, I don't know, let's call it x. Oh no, we're calling it f of y, 1, right? And it's divided by the hypotenuse, which we know to be 500. So here we have one equation, we have one unknown, which is our fy1, and we basically just solve for it. So when we solve for it, we're just taking this 500 to the opposite side. So we have fy1 is equal to sine 30 multiplied by that 500. And if you do the calculation, you find out that sine of 30, and keep in mind you have to be using degrees in your calculator, so if you're using radians, you'll get some other weird number, but if you're in degrees and you type in sine of 130, you should get 1/2. Am I in degrees? Yeah, I'm in degrees, so 1/2, 0.5. So 0.5 times 500 is 250. So we have f of y1. Okay, and now now we want to find the x component. So that component being this one here. This thing, like, okay. I'm like getting mad at my own computer. It does what it wants. It does what it wants. I saw a meme earlier today. You guys have probably seen it. It's like this kid turns around and tells some other kid that like he doesn't care that he broke his arm. But it's kind of funny because it's like he's trying to be mean. I don't know. Okay, so f of x1 in this case. In order to find f of x1, by utilizing this angle here, we can we have several ways of doing this. So we could either do a squared, maybe this side, plus b squared, this is equal to c squared. So we could do f of x1 squared plus 250 squared is equal to 500 squared. And then what we would do is just essentially solve for f of x1. And we can do that because we're treating this as a right triangle. Because this a squared plus b squared is equal to c squared, the Pythagorean theorem applies to any right triangle. So we are able to use this. But as far as using trigonometry, in this case we would be using cosine. And we would be using cosine because cosine of 30, if we look here, is equal to the adjacent value divided by the hypotenuse value. So the adjacent value, the adjacent means, so if we have an angle here, if we're looking at this particular angle on this side of the triangle, oh, I shouldn't say side, but if we're looking at this angle here, our opposite is obviously what's opposite, right? Our adjacent, or no, I'm sorry, our hypotenuse is always the same, so it's always the longest side of the right triangle. So our adjacent must be the remaining side. So our adjacent is always literally adjacent to the angle. And this hypotenuse is also kind of adjacent to the angle, but it's not considered the adjacent value. It's considered the hypotenuse. So in the equation we have the adjacent value, which is what we don't know, which is f of x1, divided by our hypotenuse, 500. So same idea. So if we solve for f of x1, we end up with sine of 30 multiplied, oh, I'm sorry, why did I do sine? Cosine of 30, sorry, times 500. And I think cosine of 30 is like 0.866 or something. Yeah, 0.866. But 0.866 times 500, right? Which is like 4 or something, 433. $433 newtons. So now we know everything. We know it all. We know everything about the components of this f of 1. So what we do next is we essentially apply the same rules to this here, and I won't get into that, but it's the same idea. The only thing is your x, so it does what it wants. So if I can click it, your x component, it literally just does what it wants. Your x component will be in the same direction as the f1 value, f of x1, excuse me, f of x1 value. So these will both be in the same direction. But what won't be in the same direction is your y component. So I think it's annoying. So notice how f of y1 is going in the positive y direction, but f of y2 here is going in the negative y direction. So we'll get some value for it. I don't know, let's say it's 3. No, it can't be 300. Let's say it's like 100 maybe. So let's say it's 100 newtons. So when you add the y components together, you won't straight up add 250 and 100, because this 250 will be going in the positive y direction, this 100 will be going in the negative y direction. So what you would do is essentially the sum of forces in y, I don't know why I was writing like that, is equal to um, 250 minus 100. So you'll get 150. So if you think about this, this value is positive, right? And remember when we went and we put this force here? So keep in mind, this is 250. And if we draw the resultant vector here, this height here isn't nearly as large as 250, but it might be in fact that this is in fact 150 or so. This is given that this is 100. But the point is that it's less. So when you go ahead and you add 433 and whatever you find here for f of x2, you'll end up with this length as the x component of the x component of the resultant force. It's pretty cool. I mean, because if I take this here, I copy it, and I subtract. So remember, tip to tail is the rule. So tip to tail here, so I come back down. So if I kind of like evenly drag this across, it ends up, they all roughly end up in the same location here, because I'm taking these two and I'm subtracting from each other, and this is where I end up. I start here, I go to here, and then I end up right here. I start here, go to here, and then I end up even further away, so right here. So we do end up with something that looks like this. So it's important to remember that what this represents is if I deleted everything, all these original forces, and had one resultant force that had properties or parameters represented by all these forces that represented my F resultant, then it would be exactly equivalent in magnitude as compared to the two that I had here. So, like in a real world situation, so this is like, I don't know if you've ever been to Elephant View. If you haven't, you should go. It's kind of nice. But if you haven't, what they have over there are, there's a bunch of people, and obviously a lot of people get stuck. So I don't know if Elephant View does it or some other people do it, but they take their huge like trucks over there, or they take like a huge I really don't even know what to call it. It's not technically a tractor, but they take like this huge truck that it's impossible to get this thing stuck in the sand, and they go and they just pull out cars and trucks out of the sand like nothing. So in comparison, it's like this is that huge truck that's just pulling this out of the sand. So you would only need this truck, this one truck in that sense. But if you wanted to use like a smaller vehicle that didn't have as much horsepower and torque or what have you, then you would need the two that we just described. So in that sense, that's exactly how something like this would apply. Okay, so once you solved for everything, once you solved for all this stuff here, for the fy1, fx1, fy2, fy2, and fx2, then what you would do to find the resulting magnitude is you'd sum forces in y, you'd sum forces in x, what do we say, 100, or no, let's say this was like, this is going to be a lot bigger, right? It'll be maybe, I don't know, let's say 200. Well, we could find it using Pythagorean theorem, but let's say that, I don't know, it's 200. Never mind. Let's say it's let's say it's 175. I like that number. I don't know. I'm just kind of being lazy at this point. What you would have is oh, sorry, that's not right. This is 433, right? Because we're taking f of x1 and we're adding it to f of x2, and that would be about 608 total. So from here, what we would do is we would redraw this. So we have our forces here, our original forces here, and then we draw something, I don't know, we would just draw a random one. I mean, if we're in paint, I mean, this is just a random one. And then we would say that this is our horizontal. We would say that the component in X for our resultant force is 608 newtons, and we'd say that the component in Y for our resultant force is specifically 150 newtons. Okay, so these are components. Let me put that on it. Is that what we had? I don't know. Okay. So these are the X and the Y components. So this one would have a value of 608. This one would have a value of 150. And from here, if you technically have a squared. You have your a squared, you have a b squared, and you can solve for c squared. And then that would give you the magnitude of your resultant force, which is what you're asked to do. So that's pretty much it for the magnitude part. As far as direction, you would say that like this is horizontal x. You would need to find this angle. So we can use SOHCAHTOA again. So or not. Okay, so okay. I hope those clicks like aren't loud in the video. Like I make this video and then I find out that they're just like super loud. So if we want to find the direction of this, what we would say is that this resultant force points blank number of degrees from the x, or from the horizontal x direction. So this force is in the horizontal x direction. It's along the horizontal direction. So this was 150. Okay, so how we would find this is, actually I need that. We would actually use tangent now. So in tangent, we have some, I don't know, some angle. The tangent of some angle is equal to opposite over adjacent. So it has nothing to do with the hypotenuse. So our opposite value, opposite of this angle here, is 150 divided by our adjacent value, which is 608. So we have one equation, we have one unknown, we want to solve for what this angle is going to be. So in order to do that, we have to take the inverse tangent. Now if you have, pretty much any scientific calculator has it. This, yeah, it even has it right here. So what you're essentially doing is, when you take the inverse tangent of everything here, you'll, in a sense, cancel out this tangent, so you'll be left with angle is equal to the inverse tangent of 150 divided by 608. So you can do this easily in your calculator. If you don't necessarily have to understand maybe what it means now, but in order to solve for this angle, you will need this. You will need to calculate an inverse of a trigonometric function. So if I could just do, did I do this right? Yeah, opposite over adjacent. So we're expecting something small, like a small angle. So 150 divided by 608, that gives us 0.24. And then if we take the inverse tangent of it, right here, they show it, we get 13.85. And I'm in degrees, so it's giving me an answer in degrees. So our angle is 13.85 degrees. Not 12, 13. Okay. So that's pretty much it as far as finding the direction. So to describe this in total, I would say is equal to, let's say, well, let me calculate this real quick. 608. Where's the squared line? Squared plus 150 squared is equal to whatever that is, and then square root 608.18. Did I do that wrong? Oh yeah, I typed in 15. Can I edit this? No, I don't think I can. (608) squared plus 150 squared. Okay, that makes more sense. 392 versus 369. So square root, so 626.22. So that makes more sense. So 622 newtons. 626, sorry. And it is located at, what did we say, 13.85? 13.85 degrees from, I don't know, positive x horizontal, or maybe you could say like just from horizontal, because this is assuming we always assume that we're when we're talking about something like this, we always assume that we're traveling in the counterclockwise direction unless otherwise noted. So the right hand rule, if you hold out your right hand and you curl your fingers inward, so you're kind of like showing thumbs up, the direction of the curling of your fingers gives you the direction of the positive direction for well, I guess this is like getting into torque and stuff. Just trust me on this. In terms of 13.85 degrees from the horizontal, what we mean is counterclockwise in this case. But it really wouldn't matter, right? Because if it was clockwise, all we would have is that, right? That'd be the only difference. So I guess it wouldn't be the same though, because positive x is still going this way. So if we say, so I guess it is valuable to say positive from positive x horizontal, I guess, or maybe even just positive x. If you have this as your answer, in my opinion, that is a perfectly okay answer for describing a resultant force. Okay, alright, that was long. Okay, so computing angles, we kind of already went over that. Okay, so as far as ethics go, like I said, make sure that you look in your book. I really haven't even looked in the book to see if there's anything on ethics, but if there is, in fact, a day scheduled later on in the future for ethics to be discussed in class, there's a really good chance that maybe the ethics portion of the engineering exam, after discussion with all the instructors, there's a really good chance that it might just be thrown out because we didn't go over it. Like, you can't be tested on something that you didn't go over. It's just simply not fair. Okay, so as far as MATLAB goes, oh, I guess it's already open. There are a few things that you need to remember for MATLAB. I don't think they're very difficult, but they're definitely easier to see, like in MATLAB themselves, or in MATLAB itself. So let me delete all this stuff here. Oh my god. Okay. Okay, so in MATLAB, this is just like a notepad. This is in MATLAB, but in MATLAB there's a few things to keep in mind. So for the exam, you'll be asked questions like, what does this thing do, or when you write this in a script and you run the program, what does it do? So some of the things that you should remember are like percent signs. So percent signs, the good thing about this programmer's notepad is that it will do exactly what MATLAB does as far as like color coding and things like that. So when you're in MATLAB in the script window and you type in a percent sign, it will turn green in MATLAB, so that's kind of good. So percent signs are for comments on code. So for example, if you have a code here, you can start it by saying that I'm defining these variables. So if you needed, like in the homework, you needed to define R, like for radius of a soda can, I think. So R would be some number, I don't know. And then you needed the height, right? So H would be also some number. And then later on, like in the code, you would say formula to calculate area of, and then you'd have like A is equal to 2 plus 2 pi r h, I think. So here is where, like, percent signs are essentially just used to tell you where in the code, like, what's happening. That way you can go back, because if you write, let's say you write, you know, a whole bunch, like maybe 500 plus lines of code, and you can't remember where this formula is, or you can't remember where you put this value, then if you go through and you look at each and every comment you made, then there's a pretty good chance you're going to find it, you're going to run into it. So that's what comments are for. When I was putting these things here, if you had a question on them, so if you're like wondering what they are, these semicolons in MATLAB are used to hide variables when you're running programs. So if you have like something like this in a script without the semicolon, in the command window, what you'll get is pretty much, you'll get something that looks like, I can't like remember for sure, r is equal to, and then you'll see like 3. You'll see something like this without this line. I don't know what the heck this is. So MATLAB will essentially just tell you what R is already, even though you've already defined it. But if you put a semicolon here and you run your script, your program, you won't see anything happen. But if you ask for R in the future, you'll get R is equal to 3. So a semicolon is just you're telling MATLAB, hey, R is equal to 3. I know it's equal to 3, but with the semicolon, you're saying, don't show it to me, like in the future. Like, I don't need to see it because I already know what I set it as. So that's what semicolons are for. So they're used to hide, I guess, to hide values of, or no, to avoid repeating, reiterating, is that how you spell reiterating? Maybe, reiterating values in the command window. My instructor called it something, and when I took MATLAB, and I like can't remember what it's for. Okay, so you have these two things so far. So next thing that you'll want to look at is what the colon operator does. So what the colon does is we'll have to look at defining a matrix. So a matrix is, it can be a lot like, maybe you guys have seen it before, but it's something like this, where you have like numbers like, I don't know, 1, 2, 3, 4, 6, 8, 11, 13, and 2. So this is a matrix. So you have here, you have 3 rows, you have 3 columns. This is ugly, but this is what we define as a matrix. So I don't know, let's just call this matrix A. So we can have something, it's essentially like a table, kind of. So you'll have a table of values in one variable, that variable being this A here. So what we'll look at is essentially nothing but, for now, we'll look at only matrices that have only one row and a bunch of columns. So we'll have something like 1, 2, 4, 8, 10, and so forth. Or we'll have something just like this. So I know, that's ugly. Okay. So now the colon operator, if I write something out like 0, colon, 0.2, or no, hold on, let me look at my notes, because I don't want to like say something and then okay, so when we're using this colon, when we're using this specifically to define a matrix, we'll have something like this. Now, like, what the heck does this even mean? So, if we were to enter this specifically into MATLAB, what we would get is I'll write it out and then I'll show you why. Or maybe you might be able to just interpret why. Let's do this. 2. Okay. So what these numbers here represent, so this first number here is the starting point of the matrix. So your first number in the matrix is 0. What this number represents here is the final number in the matrix, which is here, obviously. So initial and final. And this number here in the middle, in between the two colons, is the step size that you want to take to get from 0, the initial value, to 2, the ending value. So if you enter this into MATLAB, what you will essentially get is 0, 0.5, 1, 1.5, and 2. So that's pretty much what that does. Now, if you were to do something like just 0 to 2, what MATLAB is going to do is it's going to assume that this value here is 1. So what you'll essentially get is, I don't know what happened there. You'll get this. You'll just get 0, 1, and 2. Okay, so it's important to know what this does and its importance in making a linear or a one-column matrix. Okay, so we have some percent signs. I hope I didn't say parentheses earlier, but this is percent sign. Semicolons, these colon operators. And now if we move on to linspace. Linspace does almost the exact same thing. So what linspace does is it does generally the same thing. So like if I have like 0, 10, 100, it looks a lot the same. but these values these values are they represent different things. So what you'll get is, if I put this into MATLAB and I click enter, what you'll get is something like zero. You get like 0 all the way to 10, but you'll get 100 different values in between here. So what this number tells you, it's 0 is the beginning, 10 is the ending value, and 100 is the amount of values that you want for that matrix. So I think one example we went over in class was if you have 0 to 1 with 5 values in between, you'd end up with 0, and you can't just divide 5 into 1. You'll end up with 0, 0.25, 0.5, 0.75, and 1. And that is 5 values, right? So 1, 2, 3, 4, 5. So I guess maybe technically you could just take this number, subtract 1, and divide it by whatever this is. But it all depends what your starting number is and all that stuff. So that's pretty much what linspace does. Starting value, ending value, number of values in the matrix. I don't think there was really anything else that was super important that about MATLAB other than these here. Knowing what a script is and what the script window in comparison to the command window is also pretty important. Command window just shows you your code as it is ran. The script window is your actual code. So in that sense they're different. So one shows you what the code is doing, one is the actual code. So keep that in mind. Other than that, I don't think I can really remember anything else. But that's pretty much it. Okay. So free body diagram. So finally, let's do this kind of quickly. So let's see. Yeah, I'll just do it here. So if I have like a table here, say I have like a table, there's legs on this table. It's a gorgeous table. And then let's say on this table I have a horrible thermodynamics book laying on this table. So you're asked to draw the free body diagram of probably, for example, the textbook. So you have to know what is going on here. So it's not just simply, it is but it isn't just simply a book sitting on a table. So what you have, because gravity is acting on this book, right, which is why it's staying on the table, and which is why it's not like just getting up and floating away and leaving forever. I mean, it's not doing that. So let's draw what they are. So we have the weight of the book, and we also have the force of the table acting on the book. Okay, so these, if the book is like just standing still, these are in equilibrium, so they are the same. They are the exact same. So let's say this is 5 kilograms. I don't know if that's logical or not, but let's say they're 5 kilograms. Red. Green, sure. Yeah, okay, whatever. So the weight here, the force acting down, would be 5 kilograms times acceleration of gravity, right, which is 9.81 meters per second squared. And you also have a force normal, just like I said, which is in turn the same amount of force acting on the book in the opposite direction. So in the opposite direction, what you essentially have is weight is equal to force normal. So a free body diagram of something like this wouldn't involve the table at all. It would only involve the object and arrows. So we can start in your free body diagram. What you would have is something like your 5 kilogram block, drawn with the normal force, which can be drawn either here or here. It doesn't matter. As long as it's here and it's pointing upward. That's essentially what matters. So this is, and I don't think I have any text boxes up here. None that I left, just hang in there. So you'd have a force normal here. You'd have your weight as well. Force due to, we could call this force due to weight, or just weight. And this would be your free body diagram. As simple as it is, this would be your free body diagram of this book, because it's sitting there. I mean, it's not doing anything. Now here is where like things get a little not difficult, but here's where things change a little bit. So if we have an inclined plane or a ramp, and we put a box on it. And it's funny, like all your problems, like later on in physics, if you have to take physics, they'll all be like blocks for some reason. I mean, I don't know, maybe they're the simplest case, I guess. So here, let's actually put it here. So in this case, your block is on this inclined plane. Now the force normal is not, it's not in the same direction now as the weight. It's in a different direction. So that was a bad idea. So now your weight is facing down. Let's color this. Great. So now your weight is facing down, and your force normal is now perpendicular to the surface. So perpendicular to this surface. So, and that obviously just means that there's like a right angle here. There's 90 degrees here. There's 90 degrees in between the angle of the force normal and the surface. So that's weight, and that's your normal. That's your normal force. But you also now have one more force that you need to consider. So if you have a block here, there's a tendency for the block to fall down that way. But what's holding the block up is a friction force. So now we have that as well, and that is parallel to the surface. So if this block has a tendency to fall down this way, if it's just sitting here, it does have a tendency to fall down this way because, I mean, due to gravity, essentially. So your friction, the thing that will be holding it up would be the friction force acting in the opposite direction. So you'd have your normal force, your weight, and your friction force. Now to draw, this isn't your free body diagram. It's pretty simple, but that's your free body diagram. That's essentially it. Now, it's not complete, but I say it's not complete because of the because there's no angles labeled or anything like that. There's just you just have a bunch of arrows pointing in different directions. So if you have like this angle here, let's say this is let's call this angle alpha. This angle here will always equal this angle here. So keep that in mind. And if you have a horizontal here, line, not an arrow. If you have just some horizontal line here, the angle between the horizontal line and this friction force is also equal to what we called alpha here. So when you're drawing, if you have a problem on the exam where you have something like this and you're drawing your free body diagram, this is exactly what you would draw. So you would draw this, and then you would also draw in here the little curve sign to mean that this is an angle, and then you write whatever angle this is, and then you'd probably also want to draw the horizontal line, the little angle curve, and whatever angle it is here. So keep in mind that this angle here in between this friction force and the horizontal is the same as this angle here, which is the same as this angle here. Okay, so one more thing. As far as beams go, you may have a beam. I don't know if you'll have it in the exam, but you might have something like this, to where you'll have a beam. It'll be simply supported, which just means that it's supported at two ends. And what you'll have are a roller, a roller on one end, and a pin support at another end. So the reaction forces here, the reaction forces at this end are a little bit different than the reaction forces here. So if you think about this, this beam, let's say this was in here. This beam can slide back and forth, right? Because it can roll. It can roll on this roller, which is why it's called roller. But if this roller went here, and let's say you had this pinned down, it can rotate, like this can rotate about this point here, but it can't move in this direction because it's supported here. It can't move up because it's supported here. So what you have are resultant forces that are there's one more resultant force that you need to account for. So if I go back, let's say I have a force here. If this is just like force applied or something, your resultant forces for the, well, let's say for the roller would only be, you would only have something you'd only have a resultant force in the y direction. This is assuming that this is y and then that this is x. For here, you'd have you would have a resultant force in the y direction, but then you would also have a resultant force in the x direction as well, because like I said, this can't move. If you try and pull this way, this resultant force is gonna end up being this way, right? Because you're pulling this way, the resultant force is pulling the opposite way. Okay, so your free body diagram would look exactly like this specifically, with this being force applied. So you'd have like written force applied here, and then here you'd write, like if this was point A and this was point B, this would be your force of B. No text box. This would be your force of, this is A, this is B. This would be your force in A of X. This would be your force of A of Y. This would be your force of B of Y, right? So that's pretty much it. This is what the free body diagram is. Remember that a free body diagram is consistent of, or contains the body only. It doesn't contain anything else that's in the apparatus or whatever you may have. It's only the single object that you're looking at. So here we took out the pins because they're not part of anything. They show us what resultant forces we get, but they're not a part of anything in the free body diagram because we're only looking at the beam. In the block, we're only looking at the block and not the inclined plane or the table, so we remove those. So keep in mind that a free body diagram is of only the object itself and not anything else. I think that's, if you have distances here, label those as well. Any distances you have, any angles you have, those are to be included in the free body diagram. Any values you have, any representations of forces that you may have, those are also to be included. Like this is f of ax. Those are to be included in the free body diagram. So keep all that in mind. So after I don't know how long, I think that's pretty much it. So if you have any questions, please feel free to email me. Like I said, I have some time tomorrow. Right now it's like kind of late in the night, but if you have any questions, please email me, and we'll try to get things figured out by Thursday. So thanks for watching, and I'll see you guys Thursday.